Well, here comes 10.6. This is our last section. Very exciting. It's conic sections in polar. All right, so if you remember from 10.5, there are three conic sections we're studying: the parabola, the ellipse, and the hyperbola. And I hinted in those videos that actually all three of them can be described in just one way. And so there's kind of like, if we take a step back, they actually all have the same underlying nature. And if we just see little differences in that, then that skews the graph to be a parabola or an ellipse or hyperbola. So we're going to define, talk about each of those shapes again, and then I'll show you what they look like in polar. Okay, so starting with the parabola, and this really isn't any different than the way we did it before. But I just want to draw your attention. So the parabola, imagine a parabola. I've got it opening to the left here. It could open any direction, but this will work the best for us. So it's opening to the left, and the focus is placed right at the origin. Okay, so if my focus is right there at the origin, then some distance away is the vertex. And if I follow that same distance again, I get to the directrix, which would be a vertical line in this case. So if you remember, the parabola is defined by every point on that parabola has the same distance to the focus and then back to the directrix. So if I take that point, same distance here and there. I think my drawing's a little bit off, but you get the idea. Do this with it. Call that little line segment L1. Call this L2. So if we were to take the ratio of L1 to L2, well, that's the same number, right? So we would always get 1. And I'm going to say K equals L1 over L2, and then K always simply equals 1 for the parabola. Okay. Check out the ellipse. So what I've done here, I've drawn half of an ellipse, and you can see where I erased the other half, but we don't need that. So I've got half of the ellipse drawn. Again, I put this focus, obviously there would be two, but I put this focus here at the origin. The vertex of the ellipse is some distance away, and yes, ellipses have a directrix. They actually have two directrix on either side, but I've just got the one drawn. An ellipse has a directrix further away. So the idea is, if we were to take this distance and that distance, the ratio of L1 to L2 is less than 1. L1 is smaller than L2. So just like in the parabola, we're going to say K equals L1 over L2, and that is less than 1. Why do we say K? Because K is a constant. Any point you look at on the ellipse, that ratio of those two distances is the same, and that defines all of these points. All right. So as I pull, think of the parabola where it equals 1. As I pull the directrix away, these points are like pulled toward that focus, like the focus has more of a gravitational pull, and that pulls it in tighter. And if I kept pulling the directrix further away, it would pull it in even tighter. Okay. And finally, of course, we're going to talk about the hyperbola. So I have drawn just half of the hyperbola, just this branch, if you will. The other branch would be out here. So the focus, again, is at the origin. Okay. A hyperbola has a directrix as well. This time the directrix is pushed in closer to the vertex. So if I look at any point and I find that length and then I find that length, well, L2 is smaller than L1, so if I take the ratio L1 over L2, I get a number greater than 1. So really, what's going on? The parabola has a ratio of 1. The ellipse has a ratio less than 1. The hyperbola has a ratio greater than 1, and it all just depends on how I move my directrix around. If I push it in closer, it's like the directrix has a stronger gravitational pull, and that gets wider. As I start to pull it out, eventually that ratio becomes exactly 1, and I get a perfect parabola. This is not a parabola. It looks like one, but it's not. And as I pull it further and further away, that pulls in tighter and becomes 1/2 of the ellipse. The ellipse needs a second directrix to create the other half. And the hyperbola, well, it would have a second directrix for its other branch. Okay, very interesting. So what does this even mean? Here are the equations for any conic section in polar. Any conic section, any of the three. Circles too. It might look like r equals ED over 1 plus E cosine theta, or it might look like r equals ED all over 1 plus E sine theta. The difference between cosine theta and sine theta is which way is it oriented. Sorry for my camera here, it's just trying to find focus. Maybe that'll do it. Cosine would mean you're oriented in a horizontal direction. Sine means you're oriented in a vertical direction. Let me pull it down a little bit and get some more on the page. Maybe it won't do that any longer. Okay, let's talk about the directrix, and we'll talk about eccentricity. So if we're in this case where, let's say, our ellipse is more elongated horizontally, or our parabola is pointed horizontally to the left or to the right, or a hyperbola is doing that, then the directrix is going to be found by x equals d. So x equals, that's the vertical line. We get that number right there, d. That's our directrix. If we're talking about the sine case, then things are oriented vertically. So our directrix is a horizontal line. Y equals d. Okay. And the E. E appears twice in both forms. The absolute value of E is the eccentricity. So we only spoke about eccentricity for the ellipse and the hyperbola. Turns out parabolas have an eccentricity as well. But there, no matter what parabola you look at, the eccentricity is always just 1. So it's really not all that interesting until you realize, wow, this eccentricity is a value smaller than 1. This is bigger than 1. If you get exactly in the middle, you've got a parabola. So you can kind of just imagine the shape, of, say, an ellipse, and then you start to pull the directrix further, the ellipse would be far away. You start to push the directrix closer in, and eventually it widens out, and the eccentricity is exactly 1. Then you push it even closer, and it goes beyond 1 to the hyperbola. That E is actually the K. It's the relationship of those links that we saw back on the previous page. The value of K that was constant, that was actually the eccentricity. Okay, very cool. Note, if your eccentricity goes all the way down to 0, then you've got a circle. Very cool, very nice. All right, so what does this mean? What are problems going to look like? Can we get to some examples? Finally. Just a couple to start us off. One thing we want to practice is identifying the values of E and D. And just what's a little different, especially that numerator. So I can't fit it on the screen. Well, maybe I can for this first one. All right. So we've got r equals 4 over 1 plus cosine theta. So clearly we're in this case. Let's find the values of E and D. Well, I already have them there on the page, but let's think about it. Identify the E first. So the E is easier because it's always the coefficient of cosine theta. So here, of course, E equals 1. Then look to your numerator. Well, if e equals 1, and I've got a 4 there, then what is d? Well, it would 4 is got to be 1 times 4, so d would have to be 4, and that would all fit. And then identify which type of conic we're talking about. That you do based on the eccentricity. It's a parabola. Okay, let's look at another one. Again, I'm kind of revealing everything here at once, but let's go with 4 over 1 plus 1/2 cosine theta. Can I find the values of e and d, and then which type of conic is it? Well, e is just that number right there in front of the cosine, right? It's positive 1/2. So then I'll think, okay, if e is a half, then what is d? So 4 is e times d. Well, if e is a half, then d would have to equal 8 to get me a 4 there. All right. And then which type of conic? Well, I can just look at the e. That is less than 1, so it's an ellipse. One more for the hyperbola. What if we make it r equals 4 over 1 plus 2 cosine theta? Well, we can see the e is 2, and if I've got a 4 up here, it would have had to have been 2 times 2, so d equals 2 also. And if e is greater than 1, then I've got a hyperbola. I invite you, put these into Desmos. Put this one in first. Check out the graph. So this one, I forget, it's going to be oriented horizontally. I believe it comes back to the left, if I'm not mistaken. And it will be the parabola with a focus. The focus will always be at the origin or at the pole. Then go and put a 1/2 right there, and take a look at the ellipse. You could plot, you could graph the directrix as well, right? That would be x equals 4 is the directrix, x equals 8, x equals 2. Check it out for each one of those, and I will see you guys in the next video.